Okay, so in this lecture, we're going to work through section 3.2, which is on the product rule and the quotient rule. So in chapter 2, we introduced the first two most important concepts in calculus, that of a continuous function and that of a differentiable function. And these were based on this idea of a limit, which itself can be formulated in terms of that epsilon delta definition. So you can provide a rigorous foundation for the notion of a limit, which we explored way back at the beginning of chapter 2. So we had this intuitive idea of what a limit was, and then we made this more precise using this epsilon delta formulation. And from there, we could define what a continuous function is, and then we could define what a differentiable function is and how to compute the derivative of a function. It was defined as a limit of a different so-called difference quotient. And in working through examples of proving functions are differentiable or finding the derivative of a function, we found that the definition of a derivative was sort of cumbersome. It involved a lot of manipulation and clever tricks, factoring, multiplying by conjugates, adding, there were some times where we had, when we wanted to compute, say, the derivative of 1 over x, involved like fractions within fractions. And so it got very complicated. And so in chapter 3 now, which is what the chapter we're working through currently, and that's on differentiation rules, we want to go back to the definition of a derivative, not look at specific examples, but go back to the definition of a derivative and derive some rules for differentiation and some tools and some techniques so we can simplify calculations of derivative. So we can simplify derivative calculations, I should say. And so in the last video, we went through section 3.1, and that was on the derivatives of polynomials and exponential functions. And in the course of trying to prove that that polynomials are differentiable and that you can always compute the derivative, we deduced some general rules. So for example, we proved that if you have two differentiable functions, then their sum is differentiable. And to differentiate it, you just differentiate each function and then add the result. That's a nice rule. And we proved that if you take a scalar multiple of a function or a constant multiple of a function, so you have a function f, and then you want to you assume f is differentiable, and then you have c times f. You can prove that that is also differentiable, and you can compute its derivative by just factoring out that constant. So these are some nice rules. And so you might wonder naturally, okay, so if we can add two differentiable functions and get a differentiable function, what about when we multiply two differentiable functions? Is that also going to be differentiable? And the answer is yes. So you can, if you have two differentiable functions, f and g, and you want to compute, um, if you want to compute that, the derivative of their product, it turns out that it is differentiable. So if f and g are differentiable functions, then their product is going to be differentiable, and you can actually, there's a formula. Now the rule is not going to be so straightforward though. It's not simply the product of the derivatives, unfortunately. So let me share my screen so I can actually start writing some things down and you can see what I'm doing. So let me open OneNote. So I'm going to do a couple calculations in OneNote before we go to the book and actually go through proof. So here's um, here's I guess a theorem. So we want to try to figure out, maybe try to have some idea of what a some idea of what the product of the derivative of a product should be. So first of all, let me just state this. So if f and g are differentiable, that is each of them has a derivative, then their product f times g, of course, we don't always write this dot here, but we're just writing it to emphasize the fact that we're taking the product of two functions, then their product is also differentiable. All right. So of course, I'm not stating right now how do you actually compute the derivative, but I'm just saying that it is differentiable. So we're going to say note though, note that f the derivative, that is the derivative of their product. So I'm using this prime notation right here. The derivative of their product is not going to be the product of their derivatives. Okay. So unfortunately, it's almost never going to be true that to compute the derivative of the product, you just take the product of the derivatives. So let's look at an example to see why this is not going to be always going to be the case. So we're going to let f of x be equal to x and g of x equal to x squared. And we know how to compute these derivatives without having to resort to the original definition of the derivative. These are just going to be x to some power, so we can easily differentiate these. So first of all, um, let's compute the individual derivatives. So f prime of x is going to be 1 and by the product rule, and g prime of x is going to be 2x by the product rule. So that is going to imply that the product um, of the derivatives is going to be equal to just 2x. It's going to be 1 times 2x, so it's going to be 2x. Now, what about what is the product of the functions? So f times g at x. Well, remember, by definition, it's the product of the functions individually. So f times g evaluated at x is going to be equal to f of x times g of x. And that's going to be x times x squared, which is going to be x cubed. So that implies that if you take the derivative of f times g at x, well, you're just going to differentiate x cubed, which is by the power rule 3x squared, and that's definitely not always equal to 2x, right? So this implies that um, actually, don't have, so yeah, this implies that f times g prime is not always equal to f prime times g prime, unfortunately. But the rule is not so bad. So I'm gonna write down the rule, and it's gonna look kind of crazy at first. You're gonna wonder, why is this rule true? I'm gonna prove it, and the proof might not actually be super illuminating. So I'm gonna give a proof so that you know that this product rule is just true logically. It's logically and necessarily true. And then we're gonna look at a special case to like kind of motivate why this result is true. So we're gonna give some intuition to this result. So here's the product rule. So product rule, and this is basically like a continuation of this theorem I wrote up here. So the product rule states that if you have two functions and they're differentiable, then their product is differentiable. And not only that, you can actually compute it. There's a formula. So let's write that down. So this is going to be the product rule. This is going to be like one of the first, well, not the first most important rule. I mean, the fact that you can take the derivative of some of the functions is really important. It allows you to prove that all polynomials are differentiable. But this is a very important rule too. So if f and g are differentiable, then their product f times g is also differentiable. And not only that, um, but that we can compute the derivative. So what is the derivative of the product going to be? If you haven't seen this before, it might look odd that this is the right formula, but mathematically speaking or logically speaking, it just is. And now I'm not using prime notation. I'm going to use this. This is that Leibniz notation. So I'm just using the notation in the book. Um, so, whoops, that's kind of crazy. That's freezing a bit. Let's see. So let's see. So we have f of x, g. So what we're supposed to go here is that, but and then let's see. So g of x. So what this says is that if you want to differentiate the product, I actually don't usually write it that way. But anyways, if you want to differentiate the product, f of x times g of x, the rule says that you take f of x and then multiply by the derivative of g of x, and then you add g of x times the derivative of f of x. So you kind of alternate the derivatives, and then you add everything up. All right. So this is Leibniz notation. So here's the proof. It's going to use our trick where I can get my notes up to closed for some reason. For some reason they closed up. So it's going to use our well-beloved trick of adding in zero in a clever way. Yeah, I'm sorry about that. For some reason my browser closed, so I lost. Here we go. Okay. All right. So let's just compute this as with anything in mathematics. If you're going to prove something, you either need some res prior results that you established. These are often called lemmas. They're like stepping stones to proving a result, or you just need to prove things by definition. And we're gonna go back to the definition of a derivative to prove this equality right here, to prove the product rule. And of course, in the process, we are going to use a sort of lemma, and that's that when you take the derivative of a sum of functions, it's the sum of the derivatives, or a lot rather the limit. When you take a limit of a sum of functions, it's going to be the sum of the limits. So this will be a lemma for us. So yeah, so the word I'm using here is a lemma, and these are like stepping stones. They're still important results in mathematics, but they're usually not. They're just used to prove main results, and the main results are called theorems. So this is the product rule is a theorem. So let's go back to the definition. So the derivative of f of x times g of x is by definition, so it's going to be by definition, the limit as h goes to zero of, well, it's going to be this thing evaluated at x plus h, right? So it's going to be f of x plus, sorry, f of x plus h times g of x plus h. And then minus the function itself. So f of x plus g of x. So this is just the definition of the derivative. And now here, as I said, we're going to use our favorite trick of adding in zero in a clever way. So you're going to add. So our two favorite tricks are adding zero in a clever way and multiplying by one in a clever way. So what we're going to add in. So we're going to add and subtract the following term in the numerator. We're going to add and subtract. I think this is all we need to add and subtract. This right here. I think that's all we need to do. Yeah, I think that's all. And I actually, by symmetry, you could either do that, you could either add subtract this term, or I'm gonna guess that you can add subtract this term by symmetry. Either one will work. Let me put that in now let's say or could add, let's say, or you could add slash subtract f of x times g of x plus h. I think either one will work, but we're gonna just use this. We're gonna add and subtract this, which is of course equivalent to adding zero. So that's what I mean by saying we're gonna add zero in a clever way. So we're gonna do whoops. So this would be f of x plus h, g of x plus h. And now I'm going to add in f of x plus h, and then g of x minus, I gotta, if I add that term in, I gotta subtract it off so I don't change the fraction. Okay, and then don't forget to subtract off f of x times g of x. It's kind of getting cramped. Sorry about that. All right, so now here's what I'm going to do. I'm going to put this term, I'm going to put this right here together with this right here. Okay, I'm going to put those two together. And then I'm going to put whatever remains, I'm going to put together. Whoops, I don't know what the heck happened there. Hold on, I have a call coming in. Need to take that. Sorry about that for that interruption. So let me share my screen. So I have these two terms that I squared off right here, and I want to put those together, and then I want to put the remaining terms together. And hopefully you can start to see the derivatives of the individual functions sort of emerge. So we're going to put f of x plus h times g of x. I'll put that in square bracket. And then we have minus f of x. Sorry, that's not right. Really got to figure out why this. I just have not had time to figure out why my computer is moving so slowly. All right. So I did that wrong. So let's see. Maybe OneNote is just not the app to use. Anyway, so it's going to be f of x plus h, g of x plus h, and then minus f of x plus h times g of x. And then we're adding to that the rest of the stuff. So it's going to be square brackets, it's going to be this term minus this term right here. So it's going to be f of x plus h, g of x minus f of x times g of x. And then this is going to be all divided by h. So now I want to split these up. I want to split these limits up. Before I do that, let me just split the sum up. So I'm still taking a single limit, and then it's going to be in square brackets. So I'm going to divide this h into each thing in these square brackets. So it's going to be f of x plus h, g of x plus h minus f of x plus h, g of x over h, and then maybe big parenthesis because I'm still taking a single limit. And then it's going to be plus in square brackets f of x plus h, g of x minus f of x, g of x. And then big parenthesis here. All right, so in this first fraction, I have a common factor of f of x plus h, so I'm going to factor that out. And so when you do that, you get, so let's see, still, so it's going to be f of x plus h. I don't like that. Probably must be OneNote because I don't, anytime I use the other thing, it's perfectly fine. The when I write in the PDF itself, it's perfectly fine. Uh, all right, so I'm factoring out f of x plus h, and then it's going to be times g of x plus h divided by, sorry, minus g of x. And then this is going to be over h, right? and then I'm adding to that. So I may not make this square bracket anymore. Let me make this parentheses. So that's in the first fraction. So notice this thing right here, that's going to be the derivative of g, right? And that's good. Then I have like this times f of x plus h, but that's not so bad because if we're assuming that the function is differentiable, then it's continuous. So I can just actually evaluate when I take this limit, I can just evaluate it at zero. And that's what I'm gonna evaluate h at zero, which is what I'm gonna do eventually. If I can get this one note to work. X plus h. And then so now in the second fraction, I'm gonna factor out the g of x, the common g of x. So that will go in the front. So it's gonna be g of x. And then that will be times the fraction. Maybe I'll put a dot here also. So because I don't want this to be part of the fraction. I don't want the g of x to be part of the fraction either. So it's going to be f of x plus h minus f of x all divided by h. Now, I can at this point take the limit of this sum because the individual limits all exist because f is a continuous function, g of x is differentiable, sorry, this difference coefficient represents the derivative, and that's exists because g is differentiable. This g of x here by itself is a constant, so because we're fixing x, right? And then this right here, this difference quotient represents the derivative f, and we're assuming f is differentiable. So now I can like distribute the limit operator over it. So I'm gonna do that. So I'll basically have the same thing. All right, I'm gonna pause. I'm gonna just find something else to write in because this is ridiculous. Hold on. Okay, so let's try this using paint. All right, so this is where we left off. We had the limit. I split it over the sum like so, and now this so we have a lot going on here with this some of these limits, and then we have some products, but we're just going to deal with each one individually. So first of all, um, f is continuous, so implies sorry, that's not the order I wanted to say it. Um, f is differentiable. We're assuming it's differentiable, also implies f continuous. So that means when you take the limit as h goes to zero, for this piece here, you can just plug in h is equal to zero. Remember, that was the direct substitution property of continuous functions. That was the defining property of continuous functions. And then the last section, we saw that if differentiability implies continuity. This part right here is just going to be g prime of x, which exists because we're assuming f is differentiable. So exists because, or sorry, g is differentiable. We're assuming g is differentiable. Now this part right here, x is going to be fixed. So that implies g of x is a constant. And then finally right here, this is going to be f prime of x, which exists because we're assuming that f is differentiable. So we're using everything, every hypothesis, every assumption is being used. So now I can split it. I'll just split it like so. So this will be f, the limit as h goes to zero of f of x plus h times the limit of this difference quotient as h goes to zero over h. And then over here, I can factor out the g of x because x is fixed, so g of x is going to be a constant as the limit as h goes to zero of this difference quotient with using f, the difference quotient of f. And now I can just, because of all these observations on right here, I can just compute these limits. So this will be f of x. This will be g prime of x plus g of x times f prime of x. Or I can also write this as f of x d dx of gx. That's not, let's fix that. Oh, so g of what is that? Like a g of x plus so derivative of g of x plus g of x times d dx of f of x, which is exactly what we wanted to prove. This is the product rule here. All right, so this proves that if you have two differentiable functions f and g, their product is going to be differentiable, and the derivative is just this right here. This is how you compute the derivative. Um, so, but that doesn't really give us a whole lot of insight as to why this is the right formula. I mean, you could say it's the right formula just because that's what you proved, but let's maybe give a little insight as to why this is true. So let me pull up the book now. So here's what we're gonna do. So this is the product rule. Um, so what we're going to do is we're going to look at a special case just to get some intuition right here. So we're going to let u be f of x, v be g of x, and we're going to just assume that these are positive differentiable functions. And that's all right. That's not a huge restriction to assume that these are both positive functions. Of course, in practice, like functions could be positive, negative, all over the place. Now what we're going to do, here's the point where we're going to interpret the product of the functions. So interpret the product of the functions as an area of this rectangle right here. So u times v is the product of the functions, and so v is going to be g of x, and then u is going to be f of x. And since these are positive numbers, you can like construct this rectangle, and then the area will be the product of the functions. So now we're going to take x and we're going to just change it by this amount, delta x, some small amount delta x. And eventually we're going to let delta x approach zero because we want to take this derivative. So now we can look at the corresponding changes in u and v. We're going to use this delta notation when we compute the derivative. So just that's why we're using slightly different notation, but it's going to give us the same result. So if we look at x and then change it by a slight amount delta x, then we can look at delta u and delta v, and they'll just be this by definition. All right, so now if we change x by delta x, then we can look at we can change u and v by a small amount delta u and delta v, and this will be the area of a larger rectangle, right? So like you have u, and then you add a little bit to it, you delta u, and then you have v, and then you add a little bit delta v. And so we can enlarge this triangle just a small amount, and now, or sorry, not triangle, rectangle. And we can we can like kind of partition up the rectangle in this way. Now, if you foil this, notice if you foil this right here, you so yeah, so sorry, let's look at what's the we're not going to foil it just yet, but let's look at the change in the area. The change in the area when you just change the lengths of the side a little bit. So the change in the area is delta of u of v. Well, it's going to be the enlarged area minus the original area. And if you FOIL this out, you get u times v. So let's FOIL that out, actually. Maybe I can FOIL that out. So u plus delta u, and then v plus delta v. So you get u times v plus u times delta v plus delta u times v, and then plus delta u times delta v. So we have this delta u, but remember when we're trying to find the change in the area, we're subtracting off this delta u here. So that cancels with that, this delta u, and then all you're left with is the rest of these terms right here, which is exactly what you have over here. Delta u times delta v, so u times delta v, and then they have right here over on the far right, v times delta u, that's what we have right here. And then the last term is delta u delta v, which is what we got here. So that's why the change in the area is equal to this right here. The change in the area is equal to this right here. Now let's divide by that small amount that we changed x. So this is getting closer to computing a limit, right? So divide this whole thing right here by delta x. So first of all, we get the change in the area divided by the delta x. Then we have u times delta v delta x, and then we have this v here, so v times delta u over divided by delta x, and then we have delta u times delta v over delta x. And now here's where we're going to take the derivative. We're going to compute the derivative, and we're going to do that by letting delta x approach zero. That small amount that we change by x approach zero. This will give us the derivative of the product. Remember, the derivative delta u, sorry, the derivative of u times v is f of x times g of x. And that's exactly what we want. We're trying to find out. Trying to find out the derivative of this product. So we're taking when we take this equation right here, let me erase some of this nonsense because it's kind of cluttered. When you divide this, when you divide by delta x, when you divide this by delta x, you get this. And then when you let delta x go to zero in this equation right here, you get the derivative by definition. So the derivative of u times v, which is this product here of our functions, exactly what we're trying to find, you get the limit of this as delta x goes to zero. But now we're just taking, but this thing right here, that is this whole thing right here. So put that here, and now we're taking the limit as delta x goes to zero, and you can just distribute the limit over this sum, and then this will be a constant, this is a constant, this won't be a constant, so you can't pull it out the limit. You're gonna have a limit of these product right here. But so now you can factor out this constant here that we had over here. You can factor out this constant here, what we do here. And now you just have the limit of delta v over delta x, the limit of delta u over delta x, and then you have the limit of the product of these limits right here. But this thing right here is just by definition of the derivative of v with respect to x. So right here. And then this thing right here is just by definition the derivative u with respect to x. And these exist because remember u is equal to g of x. Sorry, v is equal to g of x. U is equal to f of x, and you're assuming those are differentiable. You're assuming they're positive also. Now, the last thing we have is this thing right here. What happens here? Well, when delta x goes to zero, it turns out that delta u also goes to zero. And let's look at why that's the case. Remember how delta u is defined. It's f of x plus delta x minus f of x. And if you're and so f is differentiable and hence continuous. So if you let delta x go to zero, that's the same thing as just replacing delta x by zero. So you would have f of x minus f of x, which is zero. So that's why you get zero and then times the derivative here, this piece right here. But that will just, this whole term will just be zero, and you're left with this right here. Um, yeah, so here, this is exactly what I was just saying. As delta x goes to zero, u delta u goes to zero because f is differentiable and therefore continuous. So this is kind of contains the ideas we use to just rigorously prove this. This is sort of a proof. It's a sort of a proof, I not maybe as rigorous as the other one, and it's also a special case, but hopefully it gives you some insight as to why this is the right formula. Um, this one right here. This is the right formula. So if this made sense to you, great. Um, if it didn't and you prefer the rigorous proof I gave before, great. If you don't understand either one, that's also fine. Proofs are can be in mathematics can be difficult and they take a lot of time and effort to understand, but that's all it takes is time and effort. You don't have to be especially brilliant to do mathematics. You don't have to be a genius. I am by no means a genius. I'm not brilliant. I just stubborn and persistent, and I want to understand these things. So give yourself some time, give yourself some grace. Um, no one understands any proof the first time they read it, especially if this is the first time looking at proofs. You might not have encountered proofs a whole lot, especially at this level of rigor. So if you don't understand it, that's perfectly fine. Just give it a little time, maybe work through the proof again. Definitely don't spend hours and hours and hours trying to understand the proof. It's better to just like try to take small bites and digest it, and then just let that like reflect on it. So that's the proof of that. Or if you want, you just who cares? Just this is the product rule, and I'm just gonna accept it as fact. That's a perfectly fine way to do it as well. But I just wanted to prove it to you because it's a very important result. So let's look at some examples. So let me pull up the paint. I guess I'll just do a new file. I want to save. All right, so let's look at this example here. So we have example one. So we want to so if the example is if f of x is equal to x e to the x, we want to find f prime of x. Wow, this is a lot smoother than one note. So this is part A, and then part B is find the nth derivative. Remember, you can take more than one derivative, and the notation we use for the nth derivative is f parenthesis n of x. So let's just think about A first. So for A, um, we're going to use the product rule. So we have this is like the first function. So let me just write down the product rule so you have it. It's always good to have product rule. So recall written down. So since we already have f, I'll use different notation. So let's say I use h of x and g of x. So the product rule says that if you take and we're of course we're assuming h of x and g of x are differentiable. So the product rule states that you take the first function and multiply it by the derivative of the second function plus I'm going to write it as now the the derivative of the first function and then times the second function. Notice I read that pretty symbol free. And it's good to when you have formulas and rules and to read them as symbol free as possible so that you can if the symbol is being reused and repurposed, you won't get confused. So the product rule states if I take the derivative of product of functions, it's going to be the first function times the derivative of the second function plus the derivative of the first function times the second function. All right, so now let's apply that to A. So we have this would be like our H, and then this would be our G of X. So according to this, I take the first function, X, and then times the derivative of the second function, which is e of x. Remember, that's that fixed point. That's that's the one whose derivative is very easy to compute. It's just going to be e to the x. Now I'm going to add in the derivative of the first function, which is going to be x, so that derivative will be 1 times the second function, e to the x. And I can factor that out, and what you get is x plus 1 e to the x. All right. Now let's try to figure out what could this be. We're going to do that by computing a couple derivatives, and maybe we'll see some sort of pattern emerge. So this was the first derivative. Oh, I'm sorry, this was supposed to be a prime right here. Let's look at f of 2, so the second derivative. So we want to differentiate this now. So we got to use the product rule again. So the product rule says you take the first function and multiply the derivative of the second function, which is just going to be e to the x, plus the derivative of the first function, which is just going to be 1 times the second function times e to the x. I'm running out of room here, so let me create some more room. All right, now if you can factor this, so you have e to the x, e to the x. So when you factor that, what's left behind is x plus 1 plus 1. So it'll be x plus 2 e to the x. All right, so let's just do one more derivative. Um, and so now we want to take the third derivative. So now we need to take the derivative of this piece right here. So again, the product rule says you take the first function and multiply by the derivative, multiply it by the derivative of the second function, and that's just e to the x, plus the derivative of the first function, which will just be 1 times the second function, e to the x. Again, I have this common factor of e to the x. I can factor that out, and what's left behind is x plus 1, or sorry, x plus 2 plus 1, so it'll be x plus 3. So note, there's like this connection between the order of the derivative you took and this constant right here. So it's like take the third derivative, so you have x plus 3. You take the second derivative, and you have this 2 here, so it's x plus 2. So this should suggest that in general, when you take the nth derivative of f of x, you get x plus n e to the x. Um, this is just a guess. This is just a guess. To prove this, you need to use what's called mathematical, oops, induction. It's a technique for proving certain statements. So basically you have all these statements, like you have this collection, an infinite collection of statements. And they're indexed by this number n. So you have like a statement for when n is equal to 1, n is equal to 2, n is equal to 3, 4, 5, 6, all the way up to infinity. And then the idea is that if you know that the statement it holds for some small cases like we do here, we proved that we proved this formula for n is equal to 2, n is equal to 3, you could even go up to n is equal to 4. And so the idea behind induction is that if you know it's true for like these so-called base cases, that's what they're literally called. They're going to be called your base cases. And then if you can prove that the nth case implies the n plus 1th case, then you know that the formula holds for every n. It's like this domino effect. If you know it holds for these base cases, and then you know that the nth case implies the n plus 1 case, then you know it holds for every n. So this is a really important method for proving. If you didn't understand that, perfectly fine. If you're curious, you can look this up though. We're not going to use that though. But I just wanted to show you tell you that that's how you justify that. All right, so let's look at another example. Um, let's see. All right, I guess let's make a new document. Oops. All right, so now um oops. So let's see. This example, I guess we could do two. So we have function f of t, and it's going to be equal to square root of t, and then times a plus b t, where a and b, uh, but actually I can a and b are real number, and they're constants. We want to find the derivative, so we're going to use the product rule. Technically, you don't have to use the product rule for this. You could distribute this term through to the a and then through to the bt, and then just differentiate each piece individually. Perfectly fine way to do it, but let's just do this using the product rule to get some practice with that. So I'm going to write this as t to the 1/2, so I know that I need to use the power rule. So now remember what the product rule says. It says that you take the first function, so t to the 1/2, and then times the derivative of the second function. So a is a constant, so that goes away, and then you have b times t, so that's going to just be times b. And now we're going to add in the derivative of the first function. So the power rule says you bring the power down, and then you subtract 1 from the power, so it's going to be negative 1/2 times the second function. And let's see, what do you get at that point? So I guess you get, all right, well, you guess you get, let's see. I mean, I guess you could just leave it at that, honestly, but I guess you could simplify it a little bit. So you get square root, so you get b times square root of t plus a plus b t over 2 square root of t. And then if you take this and you multiply and divide by square root of t, you're going to get b, sorry, 2b. Multiply this and divide by 2bt. So you get 2bt over, sorry, root t. So I'm taking this and I'm multiplying and dividing by square root of t. So in the numerator you're gonna get 2bt, and then in the denominator you're gonna get 2b root t. 2 root t, sorry, jeez. I haven't had my coffee yet, so I'm not functioning as I normally do. I also have severe ADHD, so yeah, you probably guessed that. So sometimes I talk way too fast. I try not to, and I jumble words. So I'm really trying my hardest not to. Anyways, um, so we can now just add these fractions. So we're gonna get a plus 3bt over 2 root t. And that's it. All right, so let's look at one more example, and then we'll go to the so-called the quotient rule. Now I'm not going to go through I'm not going to go through a proof of that yet because I don't like the way the book proves it. I want to first prove what's called the chain rule, which I kind of actually alluded to way in the beginning, one of the first lectures when we were talking about composition of functions. So we're just gonna look at the formula and then we'll prove the formula later on. For now, let's look at example 3. So we have example 3, and this is going to be f of x is equal to square root of x, g of x. And so this is f of x, and we're going to assume g of x is differentiable. And then what we want to do is and we're also assuming that g of 4 is 2, and g prime of 4 is 2. So what we want to do is we want to find f prime of 4. So first of all, we have f of x here, so we need to take the derivative. And we can do that because square root of x is differentiable, and square root of x is differentiable, and g of x is differentiable. So the derivative of f prime of x, according to the product rule, is going to be x to the, well, it's to be square root of x, and then times g prime of x. So first function times the derivative of the second function plus um, the derivative of the second function, which is going to be, I guess at this point we can just write it down as 2 root x times g prime, just g of x, that times the second function. All right, so now we want to evaluate this at f prime of 4. So we want to evaluate the derivative at 4, so we get square root of 4 times g prime of 4 plus 1 over 2 square root of 4 times g prime of 4. And we're given these two quantities right here, so we can actually just evaluate that. So we get square root of 4 is 2, and then we're told that g prime of 4 is 3, so 2 times 3. And then we have 1 over 2 times square root of 4, which is 2, so we have 4 times g of 4, which we're told is 2. And then that implies that we get 6 plus, I guess, 1/2. And so that would imply that this is, well, they write it as a decimal. I guess you can write it as a decimal, 6.5. All right, so now um, let's look at the quotient rule, and then we'll look at an example or two. Let's see. All right, so let me pull the book open. So there's a proof here. I don't really like it. I'll give you a better proof later. It's a like one line. Once you know the chain rule, it's really easy to prove. And that's sort of motivation to prove things like the chain rule first, because it has a lot of easy consequences. So here's the quotient rule. So we know that if you take a product of differentiable functions, the the product itself will be differentiable. And so you might wonder, does this apply to quotients? So if I start with f and g differentiable, will the quotient be differentiable? And if so, what is the derivative? Well, it turns out yes. Um, if f and g are differentiable, then their quotient is differentiable. And the formula is given like this. Now, this looks a little complicated, but once you know the chain rule, this follows from, I'll say this is an easy consequence of chain rule together with product rule. And you can avoid all this nonsense right here. This is all way too complicated, way more complicated than it needs to be. It's really, really, it's like I said, it's like one line. Once you know the chain rule, it's trivial. So what this says is that you take to take the derivative of the quotient, you have the second function times the derivative of the first function. I don't think I usually write it like this. I usually write it as the derivative of the first function times the second function minus the first function times the derivative of the second function divided by the second function squared. I think some people do low D high, high D low squared or whatever. That's perfectly fine. However you memorize it. I don't really use mnemonics. I just somehow I'm able to remember things. Whatever works for you, honestly, though. So let's work through some examples. All right, so for example, we have example 4. We have y is equal to x squared plus x minus 2 over x cubed plus 6. And so we want to find y prime. And now again, imagine doing this by definition, using the limit definition. That would be a nightmare. It would be a nightmare. Just for your own sake, write out the limit definition of this, and you'll see that it's going to be truly uphill. Don't actually carry out the calculation and try to find out what it's equal to and prove it, but just appreciate how far we've come, how much theory we've developed. Write out that definition, and even go back and write it out in terms of write out the limit definition in terms of epsilons and deltas. You'll see how very complicated it gets, and how when you develop enough theory, you can kind of sweep some of those complicated details under the rug, and you don't have to worry about them. So let's find y prime. So we have in the numerator this polynomial and this denominator polynomial. So each one is differentiable, so we could differentiate the quotient. So according to the quotient rule, you take the derivative of the top, so it's going to be 2x plus 1 times the bottom, and then minus the top times the derivative of the bottom, which is going to be 3x squared. Well, that's it. And then uh, divided by the bottom squared. And then I guess if you FOIL this out, simplify, you get, so what do you get? You get 2x to the fourth plus 12x plus x cubed plus 6 minus 3x to the fourth minus 3x to the third plus 6x squared divided by x cubed plus 6 over x cubed plus 6 squared. And then let's see now. And now if you simplify that, what do we get? So you get, I guess you get negative, so you have x to the fourth, x to the fourth. So they'll give you a negative x to the fourth. And you have this x cubed minus 3x cubed. So they give you negative 2x cubed. And then you just have a lone squared term, so this is plus 6x squared, a lone x, sorry, you have a lone x squared term, and then you have this lone x term, so this would be 12x, and then you have your constant right here, plus 6, all divided by x cubed plus 6. So kind of complicated, but way, way simpler than proving this by definition, using the limit definition, or even using going back even further and defining it in terms of epsilons and deltas. So yes, it gets complicated, but the alternative is way, way, way more complicated. All right, so let's look at another example. So that's that. This is going to be example, oops, 5. So we want to find equation to tangent line. Wait, find equation of tangent line, sorry. Tangent line to curve, the curve y is equal to e to the x over 1 plus x squared. So first of all, oh, and where do we want to find it? At the point 1 half e. All right, so remember, derivative gives you slope of tangent line. So we need to find the equation of the tangent line. We need a slope. What do you need to find the equation of a line? You need a slope and a point. You have the point, we just need the slope. And to get the slope, you take the derivative. The derivative tells you the slope. So let's get the derivative. So according to the quotient rule, you take the derivative of the top, e dx, which is e dx, times the bottom function, minus the top function times the derivative of the bottom, which is just 2x. So the derivative of 1 plus x squared is 2x, divided by the bottom squared. All right, that's good. So now we want to plug this, we evaluate at x is equal to 1. So that means our slope is going to be this thing evaluated at 1. So it's going to be, I guess if you evaluate it at so it's going to be e to the 1, 1 plus 1 squared, which is just 1, minus e to the 1 times 2 times 1 over 1 plus 1 squared. But I think you can see pretty clearly that this the numerator is just going to be 0 because you have e to the 1 times 2 minus e to the 1 times 2. So it's going to be 0. So the tangent line is going to be horizontal. So tangent line is the horizontal onto a line. Y is equal to 1/2 e. Okay. And that's basically it. So here, this is just a table of summarizing all the formulas we've learned so far. So we have this is the constant multiple, or sorry, this is the derivative of constant, which is 0, and that makes sense intuitively. Um, and then there's this power rule, and then here's the derivative of sum, and then the power rule, and so basically, like these right here together allow you to prove that all polynomials are continuous. They allow these three formulas here allow you to prove that all polynomials are continuous. Here's the nice formula about the derivative of e to the x. Here's the product formula which we proved, and then there's the quotient rule. So these are all. So we now have a ton of tools at our disposal. And the last one we want to learn is the so-called chain rule. So we took derivatives of sums. We found that if you have a sum of two functions, then their derivative is sorry, their sum is differentiable, and the formula is given right here. And then we saw that the next thing was you could ask, well, what about products of functions? If you take the product of two differentiable functions, is their product differentiable? And the answer is yes, and here's the formula. And then the next natural thing is, what about composition? That's this other operation that we have in functions. We have adding functions, multiplying functions, and of course dividing by functions. Well, what about composing functions? That was another way of combining functions. And the answer is yes. If you compose two differentiable functions, the derivative will be differentiable, and you can actually compute it. There's a nice rule, and that's what I think we're gonna do in the next section. Let's see. Oh no, not quite. Actually, we're gonna look at derivatives of trig functions. So we're gonna have a little detour first, and then we'll go to the chain rule. That's all for now.